In 4.1 and 4.2, we're going to discuss how to graph quadratic functions in a couple of different forms. And the first form we're going to talk about is standard form. So standard form is y equals ax squared plus bx plus c, where a, b, and c are all going to be coefficients, numbers, and then x and y are going to be our variables of choice. You might see them change out. Instead of y, you might see f of x, so it's in function notation. These quadratics are quadratic functions, so that would be okay. So the shape of a quadratic when graphed, they look like this, which a lot of kids refer to them as U-shaped. It is referred to, the shape is called a parabola, and it's going to open up if your a value is positive, and if this a value is negative, it's going to open down because we're going to have a reflection across the x-axis. Now back to the a value. If you take the absolute value of a, if it is less than 1, so technically between 0 and 1. So I write it like this. So if the absolute value of a is between 0 and 1, you're going to have a wider parabola. It's going to have like a 1/4, a 2/3, a 1/5, and that's going to signify that the function is increasing at slower rate, so it's going to be wider. However, if you take the absolute value of a and it's greater than 1, so 4, 5, 2.5, it's going to go up faster than normal, so you're going to have a thinner parabola. And then the very center of our parabola, the point of symmetry, is we're going to be able to calculate it. So it's called the vertex, and the x value of the vertex can be calculated by negative b over 2a. And that should be a little familiar. It's part of the quadratic formula. So the b we're referring to is this coefficient right here. So opposite of b divided by double the a. And then once you have that x coordinate for your vertex, okay, so you're going to do a little calculation, and you're going to have some, oops, where am I at? You're going to have some sort of a calculation, and you're going to get an x value right here. To go back and find the y coordinate that goes along with it, we're going to, I'm going to say unofficially, plug in this x value, this guy right here, into the function. And that's going to give you an output, which is going to be your y value for the coordinate for the ordered pair. Moving along, let's see some examples. So we're going to have a opening parabola that's a little thinner. I can tell that because the a value is 2, which is greater than 1. So we're going to have a skinny or thin parabola. And the first thing we're going to have to do is calculate the axis of symmetry. So we're going to have to calculate the axis of symmetry using our formula negative b over 2a. So negative or opposite of negative 4 is going to be positive 4. And then I just go ahead and I double the a value. Like there's no point in grabbing my calculator for this component of it. So doubling a 2 is also going to be a 4. If you're really dependent on your calculator, that's fine, but you got to know how to like type it in. And a lot of kids don't put parentheses around this denominator, and then they get the wrong answer. So anyways, I just calculated that for my vertex, the x value is a 1. That's the center point, so it's along this x equals 1 line somewhere. And because that is my axis of symmetry, I'm going to go ahead and take a highlighter, and I'm going to kind of mark up x equals 1. So I have a visual boundary for my symmetry of my parabola. That's what I really like about quadratic functions, is they're really, really symmetric. Finding this output, though, I have to go back and plug in the 1. So my formula, 2x squared minus 4x plus 3, if I put a 1 in for all of these x values, do a little calculation here, or yes, you can type it on your home screen of your calculator. The other thing you're going to be able to do is we're going to use our table feature on our graphing calculators. I'll show you on the next example what that looks like. And it can kind of help you address this issue as well. So let's see, this is 1 squared, which is 1 times 2 is 2, minus 4 plus 3, so negative 2 plus 3 is 1. Coincidentally, x and y were the same value, 1, 1. And I'm going to put that in the center of my table. Now here, you know what, let's go ahead and use the calculator now. Why not? Out of here though. So if I pull up my graphing calculator, and I go to y equals, and I type in that function, which I kind of already forgot it. So let's see, 2x squared minus 4x, I think, and then it was plus 3. We'll find out in a second. Remember how we just calculated the vertex b at 1, 1? Well, if you go to your table, which is second graph, My table's all set up stupid because I had it in ask mode. So I'm going to go to table set, which is the blue up here above window. So second window. Table start, it doesn't really matter for this. I'm going to just start it at 0. Delta table means how do you want your table to count, and 1s make sense for this problem. And then I'm going to put them both in auto mode, which means my calculator is going to autofill both sides of the table for me. Now I'm going to go to the, I hit the wrong thing. Now I'm going to go to your table. Try again. There we go. And remember 1, 1 was the vertex, so I can confirm that I must have done something right because that didn't show up as an ordered pair. The other thing that I like to confirm is that surrounding the vertex in the table should be what we call symmetrical points. So if you look right above the point 1, 1, you have the point 0, 3, and then right below it is the point 2, 3. So these 3 ordered pairs right here should have symmetry as far as the y value. So go ahead and just literally copy this table over to your paper, 0, 3, and 2, 3. And then plot, of course. So 0, 3, 2, 3, and you're going to see that beautiful symmetry. And then you're going to see an amazing feat of artistic ability, right? It's me trying to graph. Ooh. Oh, kind of jinxed myself. I was so proud on the first star. All right, so we do have a quadratic function there. It's supposed to be U-shaped. I expect a little better out of you guys because you're not graphing on tablets. I can see the axis of symmetry. If someone asked me where is the axis of symmetry, my answer would be x equals 1. That was that vertical line that split it in half. I have 3 ordered pairs plotted, one of which is the vertex. That's what I want to see on all of these quadratics. We also could extend this and ask you for domain and range. Domain of this quadratic and every quadratic that you're going to run into is negative infinity to infinity. And the range begins at the, in this case, the vertex. So remember, range is the y value beginning. So it goes from 1 up to infinity. I like to bring those old topics back, right? Feels good. All right, this next part, we're going to calculate the axis of symmetry. So x equals negative b, so negative 1, extra negative there, over 2 times a, which is negative 1/2. Now, rather than typing this whole thing on my calculator and using lots of parentheses, let's do a little bit of mental math here. 2 times negative 1 is negative 1. Sorry, 2 times negative 1/2 is negative 1. So this is negative 1 over negative 1, which is just going to come out to be x equals 1 again. So remember, now we're going to go back to the function and then plug in that x equals 1 everywhere we see an x. So we can get an output. So 1 squared is 1 times negative 1/2 is negative 1/2 or negative 0.5 plus 1 plus 4. So 5 plus negative 0.5 would be 4.5. Again, same thing. Go ahead and pause the video. Get this function typed into your calculator, please, into the y equals, and then go check out the table. And you're going to see that 4.5 is an ordered pair that shows up. And then surrounding that, you're going to have some symmetrical points. If you don't get symmetrical points, either you type the function in wrong or we have the wrong vertex. All are easy to do and fix, but we do need to be aware of that. So for me, when I look at my table, it's not what I wanted. I wanted 0 first. My points surrounding 1 are, of course, 0 and 2. And when I looked at my table, or you can even hand plug in a 0 and hand plug in a 2, you're going to get an ordered pair of 0, 4 and 2, 4. So again, I see the symmetry in the table, which means I must have done something right. The other thing I'd like to do is mark the axis of symmetry with a highlighter. Okay, or not. That didn't work. I kind of got off the line there. There we go. And we're plotting 0, 4, 1, 4.5. And I kind of forgot to discuss this at the beginning of the problem, but we have an upside down parabola here. And that makes sense because the a value is negative. It's also kind of, can you tell it's kind of wider than normal? And that's because of the 1/2. The a value going half as fast makes it kind of go wide. Domain in this case, still negative infinity to infinity for this quadratic and all quadratics we run into. The range, however, remember it's low to high. So it goes all the way to negative infinity as a beginning point, if you will. But it's going to stop up there at 4.5, which is the top of the vertex, or the top of the parabola in this case. Bracket on that, please. All right. I am trying to get this recorded before my next class. So let's skip ahead to another form. The form is called Vertex Form. So this is one of those cases in math where they're like, oh, Bob, what do you want to call this? Vertex form? Yeah, vertex form. Sounds good. Because you can see the vertex. So it's even easier than standard forms. Because instead of calculating the vertex, you just open your eyes and look. So the vertex is going to be located at the ordered pair h, comma, k. But I want you to notice the built-in negative. This is just like how we taught absolute value functions. You have that built-in negative, so you have to, quote, think opposites if you want to think of it that way. So in this case, the vertex would be at positive 4, 3. And I'm going to be looking on my table for symmetrical points, which means if I look at x equals 3 and x equals 5, I should be seeing the same output for y. So go ahead and pause to get it typed into your calculator. I'm going to go ahead and fill it in now because I already know what the answer is. So this ordered pair is 3, 4, and this ordered pair is 5, 4. So we're plotting all these ordered pairs. And the a value is a 1, so we have a very normal looking parabola. It opens up the axis of symmetry, which we didn't have to calculate, but I should be able to tell that it's through the vertex at x equals 4, because you'll notice here, if you want a formula, the axis of symmetry is just x equals h. Domain, range, we could do it all. But I'm not going to. Moving on. Another vertex form question. So instead of calculating the vertex, I should be able to just open my eyes and look for the vertex. Remember, there's a built-in negative right there. So this is a negative 3, 7. And then if I pause the video, go ahead and get it typed into your calculator. And we're going to pull up symmetrical points, which will be at negative 4, let's see here, 5. And then negative 2, 5. Negative 4, negative 3, 7, and it shouldn't surprise me that we have a little bit of a thin, but it is an upside down or a down opening parabola. Okay, apparently I need bifocal. All right. And the reason for that was my a value is negative and a 2, so that makes it thinner. That makes it upside down. It's been reflected is the official term. All right. So spoiler alert, if I graph this one, vertex would be at 3, negative 5. Pause the video to get your calculator going and typed in. But we're going to pull up symmetrical points here at 2. Now this, if I'm calculating this by hand, it's kind of gross, but I can handle it. Ready? Negative 4.5, my symmetrical outputs. And this is going to be an up opening parabola, but it's going to be kind of wider or fatter, if you want to call it that. Yeah. And I forgot to do this one on the last example, but the axis of symmetry, remember, is x equals h. So in our case, it would be right here at x equals 3, which was supposed to be there, but I did not highlight it. My bad. All right, so vertex form, awesome. Don't have to really do any calculations. You just look for the vertex. Intercept form is awesome for different reasons. If you are trying to find the x-intercepts, intercept form is amazing. A lot of kids refer to this as called factored form. So you're going to notice that anything in intercept form has this setup where someone has already come through and factored the quadratic. And the reason it's called factored form is because now you can take it further and solve and find the x-intercepts, which is when your function equals 0. So if you thought about solving each of these factors, this one would give you x equals negative 3, and this one would give you x equals positive 5. So what you just found were the two parts of the parabola that cross the x-axis. So negative 3 is the first x-intercept, and 5 is the other x-intercept. So another very important part of your quadratic function would be the vertex itself. These are symmetrical, right? So a vertex would be halfway between the two intercepts. So basically you're going to use midpoint formula. So you're going to take your first x-intercept, you're going to add it to the second x-intercept, and you're going to find the halfway point. So for us, negative 3 plus 5 finding the halfway point. Again, if you're using your calculator, cool, just use parentheses. 2 divided by 2 is 1. So for my vertex, I know the middle is at x equals 1, but I got to find the y. So this is where you go back, plug it in, a 1 here and here. So you end up with y equals 1 plus 3, 1 minus 5. Let's see, that's 4 times a negative 4. Ooh, yuck, negative 16 is your y value. Could have confirmed this on the calculator if I really wanted to. 1, negative 16, way down here. Now, you know there's no chance that if I go to draw a parabola right now that I'm going to even come close to connecting these points. So use your imagination here, guys. Imagine that I connected and made a beautiful, beautiful parabola. The axis of symmetry, remember, is at x equals the x value of the vertex, which is x equals 1 for this problem. So a lot of kids feel like that lesson kind of got easier as you went through it. Like, oh, standard form was kind of awful. Vertex form was pretty awesome. And intercept form isn't too bad either. Let's do one more intercept form just to get our feet under us here. Our 2x intercepts are where you take your factors and you solve them. So this one would produce x equals 1. This negative a in front, don't worry about that for now. It's going to come into play in a minute. And then x equals negative 3 is your other x-intercept. 1 and negative 3. And I know for my vertex, the halfway point would be when I add them together and divide by 2. So that's negative 2 over 2, which, remember, we're finding the h here. So negative 1. So the axis of symmetry is x equals negative 1. My vertex, the x value is negative 1. Those of you who are more visual, negative 1 would make visual sense for being the middle of these 2 points. But we're not done. I got to figure out what happens when I plug in x equals negative 1 into my function. So for my function, I have negative, and then negative 1 minus 1, and then negative 1 plus 3. So leave the negative in front. That's the a. This quantity is negative 2. This quantity is positive 2. So that's negative 4 times negative 1, so positive 4 is my y value. So at negative 1, 4 is your vertex. And remember how we said the a value is negative, so we should have an upside down opening parabola. Standard width. Looking good. It's, whenever I get matching questions or like an ACT multiple choice SAT style question, I'm always real happy on these because I can kind of weed my way through the answers without actually doing much work. All right, let's move on to one of my favorite problems, the woodland dumping mouse. Oh, they're adorable. They're teeny little mice with huge feet, and they kind of look like kangaroos, and they jump super far. So even though he's tiny, it doesn't matter. He can hop a pretty long distance. How far can the mouse hop? Well, the first thing I need to recognize is what form our quadratic is in. It's definitely not standard form. It doesn't have, something squared, so it's not vertex form. So it must be intercept form, which means I'm actually staring at my 2 factors. So this factor and this factor, if I set them equal to 0, I'm going to find my 2 x-intercepts. So negative 2 9 x equals 0. If I tried to solve that, don't overthink it, guys. It just gives you x equals 0. And then the other one, x minus 6 equals 0, would give me x equals 6. So if you're thinking about the context of the problem, this is the mouse taking off, bing, and then he jumps and he lands and he hits the ground over here at 6. I don't think they give me units, so I have no idea what units this is. Meters, feet, clearly not miles, that'd be weird. So the question is how far could he jump? 6, I'm going to say units. So whatever those units are, I don't know. I think it's actually meters. I don't remember. How high can it jump? Well, in order for me to determine that, I have to figure out where the vertex is. So I know the vertex is smack dab in the middle of 0 and 6. So wouldn't that be at x equals 3 somewhere? Whoops. So to figure out how high, I've got to go ahead and plug that into the function. So negative 2 9ths times 3. So that's my first plug-in. And then 3 minus 6. So let's see here. That's negative 2/3 times negative 3. Negatives cancel, 3's cancel, and I get 2. So the vertex is at the ordered pair of 3, 2. So here's the model of our little mouse. And then obviously he's not going to go underground unless he falls into a hole, I suppose. How high can he jump? That would be the y-coordinate of your vertex. So 2, whatever those units are. Precious little mouse. All right, that's our lesson on how to graph quadratic functions, mostly by hand, a little bit of calculator assistance. We will be using a lot of calculator coming up in this unit, but we can do it by hand if we really had to.